Welcome everyone to this webinar on CCUS guidelines that the EI have recently published. Hope you can see my screen here. They are the hazard analysis for onshore and offshore carbon capture installations and pipelines, and the good plant design and operation of onshore and offshore carbon capture installations and pipelines. My name's Amy, and I'll do a brief introduction to this webinar, and also alongside my colleague Eva, moderate the Q&A session later. So just before we begin, a bit of webinar housekeeping. So this webinar is being recorded, as you might have just heard, and will be made available on YouTube in due course. All participants are muted, but we want this to be an interactive session, so please feel free to post questions in the Q&A function, and they'll be answered at the end. So just a quick introduction for those on the call. As I previously mentioned, I'm joined by my EI colleague Eva, but we're also joined by Andy Brown and Prakash Patel. So I'm just going to quickly introduce the EI for those who haven't heard or worked with us before. So the Energy Institute is a professional body for the global energy industry, delivering good practice, knowledge and training across a wide range of topics and through a wide range of resources, including good practice, events like this one, like webinars and training. And to find out more, please visit the EI website. And if you're not a member already, please feel free again to check out the EI website, which you can see on screen, and see what we have to offer, as I'm sure wherever you are or whatever job or role you do, we'll have something to offer. So the Technical and Innovation Programme produces good practice guidance, and this is developed via committees made up of subject matter specialists. There are 30 plus projects commissioned each year and hundreds of published documents on the EI publication site, and this is the link to find that. The topics vary from aviation to environment, as well as CCUS, which is why we're here today, and many others that you can see on screen. So I'm now going to pass over to my colleague Eva, who will contextualize why we're here today.
Thank you, Amy. Yes, as Amy has already mentioned briefly, we have a number of committees under the technical program, and the one I look after is the one on CCUS, so carbon capture, utilization and storage. And the documents we're talking about today come under the EI CCUS committee. And the main aim of our work program is to address the scientific and the technical challenges that CCUS technologies pose, and thereby we hope to be able to assist their deployment globally. We do this by producing and regularly updating a collection of CCUS documents, and we aim for really high technical standard, which we achieve with input from topic experts that sit on both the CCUS committee as well as on the relevant working groups. And we also collaborate a lot with different stakeholders from the CCUS sector. Next slide, please. This slide shows the organization of the CCUS committee. So we have an overarching committee which steers the direction of the program, and we have 4 main working groups on flow assurance and modeling, repurposing of pipelines, ductile failure and fracture propagation, and on the revision of existing CCUS guidelines, as the EI previously worked on CCUS in the early 2010s, and a lot has happened since then, so these documents need updating. And that is exactly what happened with the documents that are in focus of today's session on good plant design and on hazard analysis. They were published in 2010 and 2013, respectively, as 3 different guidance documents, 2 on hazards and 1 on good plant design. And in the course of the update, they were restructured into 2 complementary documents, which were published in April of this year. And we are lucky today to have 2 of our experts here, which chaired the work on these 2 guidelines, and will be able to tell you more about the process of developing them and their content. And with that, I'll hand over to Prakash.
Thanks very much, Eva. Next slide, please. So, afternoon, everyone. So what I'm going to do is quickly give you an introduction to the organisation I work for and why it might be relevant to CCS. Then I'm going to go through the purpose of the documents and then provide a little bit of an insight into what's in those documents and how we put them together. Okay, so next slide, please. So, yeah, keep going. Next slide, please. That's it. So who are Marsh and what do I do within Marsh? Well, I'm an engineer. Marsh is a very large professional services organization. The bit I work in actually focuses on energy and energy insurance. So it's quite a large part of the organization, probably about 45,000 people. That part of the organization also employs a large number of engineers, about 70 to 80 engineers. So how do we get involved in these projects? Well, I'll tell you a little bit more. Next slide, please. Most of the projects, energy transition projects in general, will require some form of insurance or maybe even project finance. And project finance is not available without insurance. So typically what happens is a client will ask a broker to find insurance in the marketplace. And our roles as a risk engineer is to find out what the risk quality of that project looks like and what the details of that project look like, and present them to the market with the help of our broking and client executive colleagues. The insurance underwriters will have their own engineers and they will choose to take a certain percentage of the total risk. The size of the projects typically means that no one insurer can afford to insure a single project. So the project is often broken up into leaders. The leaders will have something like 10 to 20% of the total risk. And then there'd be a whole number of other smaller insurers would make up the total lines in an insurance policy. So that's our role very quickly and why we're involved in carbon capture projects. So next slide, please. Okay, so a little bit of a history about the documents. Back in about 2005, 2006, what was, I think, the Department of Trade and Industry, which subsequently changed its name to another department, asked the health and safety executive what they thought were the main risks or uncertainties and health and safety implications of the proposed carbon capture projects of the time. The health and safety executive had quite a long list of concerns, but if you grouped them, they were grouped into two broad areas. One was the dispersion of carbon dioxide should there be an incident and how that should be modeled. And the other element was the existing industrial gases industry had quite a lot of experience in managing and transporting carbon dioxide and producing carbon dioxide. So the health and safety executive were concerned that that information should be transferred to what was really a small or non-existent carbon capture industry at the time. Okay, next slide, please. The industrial gases industry at the time were very used to designing carbon dioxide capture plants and liquefiers. And what you see on the slide in front of you is an example of that, with the capture plant on the right, a typical amine unit, probably an advanced amine unit for the time, and then the CO2 liquefier on the left, and about 1,000 tons of carbon dioxide storage. Next slide, please. So those industrial gases plants were typically very well designed. They were designed to be operated by a single person during a typical shift, an 8-hour shift. The same individuals, particularly on this plant, also were the maintenance team. The maintenance team knew the plant very well, and they also had operating knowledge, so their knowledge was actually quite detailed. They could work out what the problems were and how to fix them. And they identified, on a typical industrial gases plant, they identified lots of issues that perhaps would not have been identified by a single discipline. Okay, we also in the industry, I worked in that industry at the time, had figured out how to design vents. So if you look at that picture on the right-hand side, you'll see a lot of vents, which are carbon dioxide vents, including the ones on top of the main structure there in the middle of the picture. We also had figured out how to disperse liquid carbon dioxide, which is what you're seeing being dispersed, and you can see that as sort of showing up as a cloud of water vapor. So we were pretty confident at the time that we knew how to manage carbon dioxide dispersion. However, the commercial tools available at the time required some manipulation, and in particular, the source term had to be modified. So there was some work to be done. and we documented everything that had been learned in the design and operating phases and the safety elements in the original guidance document. However, okay, that was 15 years ago almost now. So next slide, please. Okay, and again, next slide, please. So in the intervening years, other companies had carried on working on projects and were developing projects. A typical project looked something like this. There was a capture plant, which on the whole is out of scope, but we do describe the capture processes and methods within the two pairs of documents, sorry, in both documents. The other parts of the scope that we included were the intermediate storage, compression and pumping stations, as well as pipelines onshore and all the way to the wellhead. So companies have carried on, and they've learned quite a lot in that intervening time period, including the impacts of impurities on the transportation of carbon dioxide and potential requirements to come up with new equations of state. Okay, next slide, please. Okay, so a little bit more detail about the documents themselves. I'm going to cover the guide to hazardous analysis, and Andy will cover plant design and operations. The hazard analysis document contains the items you can see here. I'm going to not go through the legislation element of it in detail, so I'm just going to cover it here. At the moment in the UK, the Health and Safety Executive has really not decided to designate carbon dioxide as a dangerous fluid. However, throughout the document, we encourage people to treat carbon dioxide as a hazardous material. Around the world, we've also covered the legislation in the EU and the US. In general, we would recommend that the carbon dioxide is treated as hazardous materials and designed like any other hazardous material plant. Okay. Other elements of the content I'm going to cover now in the slides that follow. So next slide, please. Okay. What we have tried to do in the document is to try and help potential operators and designers to focus on the risks of the processes that might be developed. In general, what we've tried to do is identify the hazards and how those hazards might be mitigated. And the documents, the hazardous guidelines document generally follows that path throughout and is structured that way. Okay, next slide, please. Okay. In order to understand the hazard, one of the fundamental requirements is to understand the physical properties of a material. So we spend a lot of time looking at the physical properties of carbon dioxide, particularly how it is supercritical and the implications of it going supercritical under certain operational conditions. We also look at how the material might go solid and the impacts of that and potential hazards of that. We talk a little bit about the uses of carbon dioxide to provide context as well. Okay, next slide, please. Trying to switch my phone off. Okay, so once the properties of carbon dioxide are understood, then the hazards, while it's being processed, are a little bit easier to understand. So, for example, if you realize that carbon dioxide can go solid, it can end up being about -79 in process plant, then it becomes apparent that carbon steel plants could become brittle. And it provides guidance on how to prevent that situation, and should it occur, how to handle that situation. And it points to guidance in the industrial gases industry that deals with specific issues of solid formation in a vessel. We know carbon dioxide is acidic, so how to avoid that risk in terms of keeping the carbon dioxide generally water-free or free of conditions that could result in corrosion. It's not just about free water, but the availability of water within the process. We cover things like running ductile fractures. You can see that in the bottom left picture, and what that might look like, and the impacts of that in modeling releases of carbon dioxide. We cover things like bleve formation. Bleves are not thought of to occur in benign materials or non-flammable materials, but in the cryogenic world, they can happen. And there have been a couple of incidents in probably about last 50 years where carbon dioxide vessels have levied, and on at least one occasion there were fatalities. Okay. Another thing that might not be realized is that carbon dioxide is actually toxic at high concentrations, around 10–15%. It can become fatal if the exposure is more than a few minutes. When carbon dioxide becomes supercritical, typically that is above about 80 bars and about 32 degrees C, it can penetrate elastomer seals, and should the pressure be taken off very quickly, those seals tend to destroy themselves as the carbon dioxide cannot escape fast enough. Okay, you can see pictures of that. The top three pictures show that. On the bottom right is a carbon dioxide pipeline failure. It's a 24-inch pipeline failure. And that particular incident resulted in a cloud rolling down a slope and impacting a town, probably about a kilometer away. And that sort of demonstrates the sort of toxicity or potential toxicity of carbon dioxide. Okay, next slide, please. Okay, the document includes example scenarios that should be modeled in a typical project. And we've got a number of results that we've shown. I'm not going to go into a huge amount of detail. They do come with a bit of a warning that each project should develop its own scenarios and model them independently to make them project specific and not to rely on the information provided in the results provided in the guidance documents. Okay, next slide, please. When we went through the work process, we were not able to model everything and provide examples of everything. So we do plan further work in the areas of underwater releases, and also to account for slopes and other topography that we need to account for in a typical carbon dioxide dispersion. Okay, so that's outlined in the document as well, and that program of work will be ongoing, and this the hazardous guidance document will be updated in the future. Next slide, please. I would say that one of the most important sections in the document is looking at previous incidents and the behavior of carbon dioxide and learning from them. So we cover a number of incidents. On the top right, you can see a typical, a cloud that might form. It's relatively dense, relatively low lying. The water vapor that you're seeing there doesn't really necessarily indicate the extent of the hazardous cloud, but it does show the sort of shape of it. Bottom left, you can see a release from a CO2 tanker, and you can see that the low temperatures that have developed around the car and the base of the tanker, indicating that low temperature embrittlement really is a hazard that needs to be borne in mind. That tanker is probably only about 20 tons in liquid content, and a typical plant may be able to discharge much more than that at low temperatures. The picture on the top left is a CO2 pipeline failure, I believe, and that's again just another example of an incident. The picture on the right shows that the incident I showed earlier on an earlier slide, the Sarnia incident, Sartesia incident in Yazoo County, and what that shows is the topography and why it's important to perhaps think about modeling slopes should there be a carbon dioxide release. Okay, so I've quickly gone through the contents of the hazards document, and I'm going to hand over to Andy, who's going to cover the good plant design.
Thank you, Prakash. That was that's a very good run through of the document. So, I think one of the problems with carbon capture and storage is this. To many people, this is a new technology. So this is a document that we wrote to capture, if you want, a great deal of what we know about carbon capture and storage. So for the mechanical engineers, some of the bits on why we intercool compressors, for instance, that will look a bit tame. But for other people, there will be a opportunity for a light bulb moment. And for chemical engineers, some of the chemistry in there will look a bit naive, but for other people, it will be help to understand what's going on. So, can we have the next slide, please? Yes, I need to describe progressive energy. Well, yes, we are, for whom I work, we're a low carbon energy projects company. We've been around since 1998. We've focused on low carbon solutions, and we have a number of projects under our belt. If you go to the next slide, there are some of our projects here. Our main project has been the HyNet project, which is in the northwest of England, where we are taking the waste gases from the Standard Oil refinery. We are effectively taking the hydrogen out of them and giving them back to the refinery so that they can recover the calorific value of those gases. And we're converting the rest of the carbon dioxide, which we're taking by pipeline into the Irish Sea or Liverpool Bay, where it's going to be stored for long periods in the strata that used to contain the natural gas. We're also involved, and having got that carbon dioxide infrastructure in place, there is scope then for other people to add their CO2 to it. We're also involved in HyDeploy, which is looking at how much hydrogen we can put into natural gas. We're looking, we manage the industrial fuel switching project, which takes real life situations and substitutes for hydrogen for natural gas. And what you can see there in the penultimate picture on the right-hand side is a glass-making furnace at St. Helens that's operated by Pilkingtons or NSG. And I have with me a piece of glass that was manufactured using hydrogen. And Grinion is a green energy company. That just gives you an idea of the sort of projects that we're involved in and are developing. But that's the commercial bit over and done with. Can we have the next slide, please? So, as I was saying, we get excited about carbon capture and storage because it's not the answer to global warming, but it's certainly part of the solution. And the reality is that we need all the CO2 mitigations in our toolbox, and that includes carbon capture and storage. If we're going to get a handle on global warming and the things that cause it, we're going to need everything in that toolbox on the right and a lot more besides. The attraction, if you want, of CO2 capture and storage is it's available without developing or scaling up, or not scaling up by much, any new technologies that makes it readily accessible, and it's there to make significant differences in things. You've heard about the Energy Institute separately already from Eva, so we can move on to the next slide. So here we are. This is the slide that says it's here to help people to widen their knowledge and to understand more about carbon dioxide storage. It also provides a technical reference to the hazard analysis guideline. And they are both structured such that if you have them both in software format, there are links between the documents. So that instead of sending you scurrying away to find another document to look at, you should be able to click it and it'll bring up the relevant part of the other document. So they are separate documents and they do stand on their own, but they're also closely interlinked. So that's the target audience and the structure of the documents. Next slide, please. So the scope is of this document. This includes CO2 capture, which we'll talk about in a minute. So we don't say too much about the CO2 sources because those can be many and diverse. So we start with a source producing CO2 of some sort. And we talk about how the CO2 is captured, and we'll look at in a minute at the various options that are available to the designer. And having captured the CO2, we talk about how it is cleaned and compressed, or compressed and cleaned, or both. It goes through onshore CO2 transportation, not just pipelines. It talks about other forms of transportation as well. We talk about pumping and compression that could be after transport. We talk about offshore transportation without going into lots of details about ship design. And we talk a little bit about what happens offshore. There are certain exceptions to that. For instance, offshore platforms are not included in the scope. And we finish when the CO2 essentially disappears down the seabed. So it's got quite a big scope, but there are gaps. We're aware of the gaps, particularly in terms of the offshore platform bit. There are moves afoot to try to cover that, or to plug that gap. Next slide, please. So here are the contents. So we really work through the whole chain that you've just seen, with capture, compression, conditioning, transport, injection facilities. We talk about storage because if you're going to transport the CO2 by ship, you will most likely store it local to the port. And when you've got a shipload, that's when the ship arrives. And then when it discharges at the other end, it will probably discharge it into storage so that you can let it into the onward infrastructure at a controlled rate. We talk a little bit about carbon dioxide utilization. And then we talk about, Prakash mentioned the need to develop new equations of state. And there's a section here that talks about the equations of state and gives an introduction to another paper that the Institute has published that is specifically on flow assurance, which gives guidelines as to which equations of state are most appropriate depending on the impurities that you're dealing with. It talks about measurement, and we talk about plant design operation. Obviously, within that, there's all sorts of subsections, too many to fit on a single PowerPoint slide. Next slide, please. So, for the CO2 capture technologies, we limited ourselves deliberately to those processes that are commercially demonstrated. We're in a happy situation where there are many, many different processes being developed, a lot of them at laboratory scale. And there are so many that, because this is meant to be a guideline to projects that we are building today or that we will build in the near future, we've limited ourselves to those processes that are commercially demonstrated. You see from this slide here that there are 5 main groups. There's absorption, which is by chemical absorption, very often amine based. Physical absorption, which is more appropriate when you've got dealing with CO2 at higher pressures. There's cryogenic, which is a technique which is favored by the Industrial Gases Company. There's membrane separation, which they're kind of borderline commercial at the scale that we're looking at, but shouldn't be dismissed. Then there's adsorption, which is similar to absorption. Then there's chemical looping, which is being piloted at the moment. So there are quite a few different technologies. Some of them are not quite ready for big scale up, but they're all commercially demonstrated. Next slide, please. I think that's the best way of presenting that, and to deal with everything else as the questions, because that will raise things that are of specific interest to you. Just before I finish, I would like to say that earlier today I was presenting to an audience of engineers who support the insurance industry, and they are being asked to provide insurance cover for plants that with which they are not familiar. And this, I had to recommend to them that they get hold of a copy of this Energy Institute book, because it will give them a lot of the background information they need to make their own assessments. Thank you.
Thank you very much, Andy and Prakash, for giving your presentation. So we're now on the Q&A time, and we've got a question already come in, which I'll ask in just a second. But just to everyone, please feel free to post your questions either in the Q&A function, or you can post them in the chat. So we got a question already come in, which says, this question is regarding document scope. Is there a separate document that covers risks and design guidelines for subsurface storage?
I'm going to start off, and then I think maybe Andy can chip in. But we are thinking of providing a separate document that will cover the hazards element of that, I think. And I don't know if there's going to be any work done on the detailed design. Maybe, Andy, this is a question for you to chip in on, based on your connections with the HSE.
I think because the geology of stores is not homogeneous, it's very variable in every conceivable way. It's not the same area, it's not the same shape, it's not the same topography, it's not the same depth. The characteristics of the rocks vary from store to store. Some stores have got penetrations going through them to access the natural gas underneath. Some stores are completely virgin. It's very difficult to produce a single set of guidelines. Some stores are only a few hundred meters deep. Some stores are kilometers deep. So this would be a very difficult document to put between two covers, because there's well over 100 different stores available or potentially available in Europe. So to try and get them all together into a single document. The other thing is that the stores, some of them are very well characterized. Where the store has been used, where it's a depleted natural gas stores, it's very well mapped. We know a lot about it. Where you've got a saline aquifer, we don't know very much about that particular saline aquifer, because we've never needed to find out. So the scope and variability makes it very difficult to envisage such a document. I know that one of the questions people will ask is what happens if the CO2 escapes? And for this, we need to get the right picture of what a store looks like. And a lot of the drawings that you will see if you Google CO2 store, they look like a cave sandwiched between some rocks. And it's not like that at all. I'm just going to... reach. It's a question of, here's one I prepared earlier. The CO2 is actually stored in rock. This is a piece of bunter sandstone, and the CO2 is stored within the pores of that rock. And over long periods of time, the CO2 will react with the rock to produce carbamates, which are solids. So, if we were to get a geological disturbance on day 2 after you've just finished injecting it, you may get some CO2 that reaches the surface. If it happens in year 602, then a lot of the CO2 will have reacted, and there won't be so much gas to escape if you want. But just bear in mind that these stores have been there for geological lengths of time, and most of them have previously contained natural gas under pressure for that time. So I'm not saying that the stores are without risks. What I'm saying is that the risk, it's not a high priority right now to start looking the stores, but to try to envelope them all between 2 covers, it's a very difficult job.
Yeah, and just to finish off, we are in my world, in the insurance industry, what we're seeing is what Andy's had just explained. We see bespoke analysis of every store, and that's actually a sort of a mandatory requirement actually coming from a lot of the legislation that we're also seeing as well. So each store has a bespoke risk analysis and technical evaluation that has to be done before it is utilized. Okay, probably time to move on, Andy.
Well, thank you for your answers. So we got another question saying, there are several proposed and ongoing JIPs that are addressing various outstanding issues with CCUS. Is there a section in the reports that talk about knowledge gaps and areas where further research is needed, perhaps mapping across the JIPs? And they said they appreciate it's a challenging and rapidly evolving topic area. But yeah, what are your thoughts on that?
Well, I think certainly the hazards document outlines areas where there are gaps in our knowledge, particularly around modelling of subsea releases or subsurface releases. There's also things that we've learned in recent incidents in the last 2 or 3 years as we're writing the documents around, for example, that release in Mississippi, where some regions do not treat CO2 as a hazardous material, and perhaps there should be plans for emergency response, and guidance on emergency response is probably one of the areas that probably needs further work. As an example, that comes to my mind. Andy, do you have others?
Yes, we haven't listed the JIPs as such in the document, but we do acknowledge that there are gaps in our understanding, particularly of the behavior or interaction between impurities. The document points out that what is happening is people have taken a conservative approach to that, pending the arrival of good quality information. So we've not used this as a vehicle to identify these gaps. As Prakash says, one of the problems we've had is this has taken about 4 years to write. And some of the gaps that we started off with have been plugged during the course of the 4 years, until eventually we had to say, stop. We're going to stop it. We're not going to update it anymore. We're now going to publish it. And somebody else can do an update sometime down the line.
Yeah, and just to build on what you said, where we've found the work had been finished, we've referenced it so you can read about it rather than trying to cover it within the documents. Okay.
Yeah.
Brilliant, thank you. So we got another question. What level of efficiency can be realistically achieved in the CO2 capturing process?
Yeah, I'll have a go, and then Andy, you can perhaps build on it. But the answer is it depends, is the honest answer, because it depends on where you're capturing it from and the technology that you're using. So in my world, in the insurance world, I've seen efficiencies of around 95 to 99% quoted, okay, using different processes, which I won't go into details on. Andy, what are you seeing in your world?
Well, VAT in the UK has been assessed as 95%. So we can expect 95% across the road, across the board, or better than 95% capture. I think that there will be a difference between what a manufacturer or a vendor will guarantee and what is actually achievable. Because if he can achieve 97, he will probably only guarantee 96. And then if you get to 97, you'll be pleased. And it also depends how much you're willing to pay. So if you're willing to pay for 97%, then you might get that. If you want to pay a bit more and choose a different technology, you could get 98 or 99%. It's a good question, but it's not one that's easy to answer in a handful of sentences.
Fair enough, thank you. So there's another question here which says there's very little experience of post-combustion carbon capture. Most indicate substantial underperformance and greater energy penalty should be expected. This is particularly the case under intermittent load, as with dispatchable power, and variable fuel, as in energy from waste. Does this make insurance problematic?
Okay, so I'm reading the question again. Okay, so I'll start with it. I guess it's probably one I should answer. So if we just frame it as relatively new and immature technology, then insurance will require more scrutiny and more explanation. And, you know, the insurers in general will be looking for how the technology has been developed and how it's going to be upscaled. And they'll be looking for reference plants, which is something really difficult. Okay, so that does become a challenge, but it's not impossible. The insurance industry, the insurers in general are positive about ESG, okay, in general, and they have a commitment to supporting the energy transition. So it could be difficult, but I would not say impossible, okay, is my general summary of pretty much all of the energy transition technologies, and that includes post-capture combustion, okay. Andy, anything else to add to that?
Yeah, capturing CO2 has been around since the early 1970s, when it was used to remove surplus CO2 from natural gas. So it's not a brand spanking new technology. I think the point is well made that chemical process plant works best at steady state conditions. It doesn't like being ramped up. It doesn't like being turned down. It likes sitting there. And the reason that high availability is obtained in the industries like the refining industry is they start it up and they don't shut it down for maybe 4-6 years. And it just runs flat. And it's very happy doing that, barring all sorts of things. But that's the way to run a processing plant, to start it up in the morning to cope with the morning peak and then shut it down in the evening is an onerous duty cycle for these plants, some of which operate on quite tight margins. If you take something like an air separation unit, that actually operates on quite small temperature differences. And ramping it up and down, you lose purity. And once you lose purity, you lose efficiency. And that is the case. And dispatchable power is a challenge. And I'm interested to know, to watch to see how the Teesside project works out.
Yeah, just to add a little bit of colour to Andy's comment on air separation unit, that, you know, the delta T's can be little as 3 Kelvin. When you're operating a plant at around -180, that's quite a small temperature difference. And if you're operating a plant at that lower temperature, shutting it down and getting it cool again could take you 36 hours. So that's not really viable. Okay, and then I guess the same thing applies to amine units, where you don't want to stop circulation. You might want to minimize circulation, You definitely don't want to stop circulation on a regular basis because similar things can happen in terms of temperatures. Okay. Okay.
Okay, great. We had another question, quite a short one this time. Carbon dioxide utilization was mentioned briefly. What particular type of CO2 use is covered in the documents?
I was responsible for this. What it says is that the problem we're looking at on a global scale is gigatons of CO2, and CO2 utilization can make contribution to reducing it, but it's not the focus of the document because we've been looking at carbon capture and storage rather than carbon capture and utilization. But there is a chapter on utilization, and it does talk about some of the ways that it's used. It also challenges some of the assumptions that are made, such as enhanced oil recovery, which it says is not true carbon capture and storage. But you'll have to read the document if you want to disagree with me.
Again, to build on Andy's comment, using it for enhanced oil recovery may be one of the main usages I'm certainly seeing in my world. But there are other usages that are probably not true usages. For example, I've seen it used in greenhouses, for example, to enhance growth of plants. Okay, just as examples, but it's not large scale. And I agree with Andy that beyond perhaps oil recovery, it's probably not going to have a huge impact on our carbon dioxide reduction. Okay, Andy?
Yeah.
Okay.
Okay, great. So we got a few more questions. So one of them is, how can designers or system operators deal with unresolved knowledge gaps and gain stakeholder approval to their plan designs or operations? E.g., do they embed more conservatism, e.g. larger separation distance or other control measures than for established or mature knowledge and technologies?
So from a hazards, I'll go from a hazards point of view. Yeah, you do need to perhaps make allowances for uncertainties. I'm not sure it's always conservative, but you have got uncertainties and you've got to define what those uncertainties are and put a barrier or a framework around those uncertainties and explain how you're going to resolve them. From an engineering point of view, we've been doing this in process design for decades, okay? We don't have all the information and we design a new process. So a prudent approach, a cautious approach makes sense, but not necessarily so conservative that the project is not viable at all. Okay, you can't take that approach, and we haven't in the past, to be honest, either. Andy?
Right, I've got nothing to add. You've captured it very well there, Prakash.
Okay, thank you.
Thank you very much. So we've got a few more questions. I'll probably pick a couple which we'll answer. So there's one here, short one here. As CO2 has to be quantified for carbon credits, how is this done on ships?
Okay, so I'll start, and again, Andy can chip in. I've seen a few projects where carbon dioxide is going to be, transported by ship and then sent to a subsea sequestration site. The key issue here is usually is contracts between the various people involved in the chain. So it will be, the emitters, the transporters, and the sequestrators. They'll all be interlinked via contracts, and how those contracts work and where the ownership switches is really the key issue, I think. So it's not just about it's on a ship, it's about who owns it when it's on a ship and then who owns it when it's being injected. So that's what we think from an insurance point of view. Andy, anything else to add?
No, only to note that politics comes in to complicate things. And as things are in the post-Brexit world, any CO2 that you capture on mainland Europe that you ship to the UK doesn't attract credits in Europe. There are moves afoot to untangle that, but as things are at the moment, there is no commercial benefit in capturing CO2 on mainland Europe and exporting it to the UK. It just shows that how politics can come in and muddy engineering waters.
Yeah, good point.
Yes, I think we'll do one more question so we don't keep over time. So there's one question here that says, from the conversations that this person has had, it seems like there's some uncertainty about toxic thresholds for CO2, which to use and when. Have you reviewed these thresholds in the hazard analysis document, or do you think this could be reviewed in a future document?
So I'll start, and I know Andy may have a comment or two on this. So we have used what was provided by the HSC. We reviewed what was available. There is, I think, some uncertainty in the values used, and particularly offshore, for example. The slot data might be more representative in terms of impact for vulnerable people, perhaps, but less vulnerable people and workers, it probably needs a bit more work. And just by way of example, we know, for example, the US Navy has higher tolerance limits for CO2 in submarines, just by way of example. Okay, then perhaps we would allow for in our calculations for safety reasons and impact on the general public. Andy?
That's absolutely right, Prakash. What we have to remember is that in a carbon capture and storage context, we're not dealing with pure CO2. We're doing a CO2 with levels of impurity within it. And some of those impurities will be toxic. So if we take H2S, for instance, it's not just the smelly gas. It can numb your senses and it can eventually kill you. How do we deal with H2S? And the way that it is being dealt with by the industry, and this is something which is embodied in the ISO standard that relates to CO2 transport, we keep the level of those toxic compounds down to a level such that in the event of an incident, the CO2 itself is the dominant hazard. Now that means that when the emergency team, in the unlikely event of a release, when the emergency team responds, they know that they're walking into an environment where the hazard they have to be concerned about is the CO2. It's not in the COS. It's not in all the other stuff in the CO2 because that's at a sufficiently low level. So that's another angle on it. And I think my appeal to everybody is to realize it's easy to think in terms of CO2, but we've got to think in terms of the CO2 stream, as we call it, which is a CO2 with all of its impurities at controlled levels, because the characteristics of the two gases are not the same. And my other appeal is that CO2 is not natural gas. To me, one of the biggest concerns I have is that people say, oh, we know how to deal with natural gas. We understand natural gas. CO2 is just another gas. And the important thing is it's not. It is a very different gas. And it's not pure. And the fact it's got impurities in it promotes some interesting characteristics, which you can read about when you buy the book.
Okay. I can answer one more question if it helps. It's from James Hewitt. I've got do we have time to do that?
Yeah, I think we have time for one final question. Yes, go.
So I do happen to know that the UK government's stance is that in terms of leakage and site, licensing sites, what they expect is that wherever possible, the commercial insurance market is utilized. Okay. That's their position, and that should be incorporated into projects, is our understanding today. That might change, but that is the current position. So that means that the remainder of the risk then is probably owned by the government and the UK taxpayer. That seems to be the position at the moment. However, obviously, all things can change. Okay, I hope that sort of gives a flavour, James.
Brilliant. Well, yeah, thank you. We're just coming up to the hour now, so we don't want to keep anyone any longer than they originally planned to be here. But I just wanted to wrap up and say a massive thank you to Prakash, Andy, and Eva for their time today, for answering all your questions and presenting this work. We also want to thank everyone who attended, because you're the one asking the questions, you're the ones hopefully getting and reading this guidance as well. So if this webinar was of interest, please feel free to check out the EI publication site and, you know, get this publication or publications. So just a little plug from me. We do have another webinar in this series in early July. It's on a kind of different topic, but if it's of interest, please feel free to check out the EI What's On page for this. Yeah, so just want to say thank you again, and I hope you have a good rest of the day. Thank you, everyone.
Bye all. Bye.
Thank you.